Okay, this is one of those difficult physics problems. One where it takes a lot of physics thinking to set it up properly. So here's a bicycle tire. It's going over a curb. And the question is, how much force does it take to bring this wheel up over this curb? First of all, you could imagine that if the curb was so high as to hit the wheel flat on the front, so when if the curb was to the height of r, you would never get it over. Well, actually, we'll get into that later. So here we are. There's a force. Let's ask, why will it ever make it over that curb? And when it does go over that curb, what is it really doing? Let's think about it as it just starts to rise over the curb. The only point that we'll be touching is that point. It's going to lift off of this level, off of this ground level, and it's going to pivot. The question is, what force does it take for this wheel literally to pivot around that point? This is actually a torque question. The effective lever arm is there, and this wheel will pivot around that point. There won't be any spinning of the wheel at all. It will be a pivot, and then it will start to roll once it's rolling along the surface. But until it rises up to the surface, it's going to be just, it hits, and it's a direct pivot over that surface. Alright, so there's effectively a lever arm from that pivot point to the center of the wheel. And if it's going to pivot at all, this force working to pivot the wheel, this is clockwise, is going to have to work against, well, what's the force that's keeping it down on the ground? It's this weight. So there's a weight of the wheel holding it down, and it doesn't actually mention a weight, but I can only assume that there is one. Oh, it has a mass. It's given a mass. So weight is equal to mg downwards. So I will eliminate the weight symbol and just put mg. Actually, no. I'm going to leave the mg and keep the weight there. Weight is the force. Let's leave it there. Okay. So in order for there to be a torque, we know that there is going to be a net torque. The net torque is equal to torque 1 plus torque 2. Let's call this one torque 1. It's going to be equal to the, well, let's remind ourselves what torque is. Torque is equal to a perpendicular force times a lever arm, or a force times the perpendicular part of the lever arm. I'm not sure what's going to be easier. I think maybe this second one. Let's think about it. What's the torque caused by this force? We can either talk about a part of this force perpendicular to this torque, or talk about part of this lever arm that is perpendicular to this force. I like that one actually better. I'm going to bust up this lever arm into a horizontal portion and a vertical portion because I have a horizontal. So let's go with lever arm X, and let's consider lever arm Y. And we'll just leave this as the lever arm. Lever arm, first of all, the lever arm length is equal to the radius of the wheel. Lever arm Y is equal to the radius minus h. Radius minus h. And this lever arm X, I can use Pythagoras to figure that out. Let's see, I have L squared is equal to Ly squared plus Lx squared. That's Pythagoras. L squared is R squared is equal to Ly squared, which is R minus H squared, plus Lx squared. I don't know what Lx is. That's what I'm trying to find out. So I can see that I can minus this from both sides. R squared minus R minus H squared is equal to Lx squared. I just moved this part to the left-hand side, trying to isolate for Lx. I can take the square root now. Square root of all of this is equal to Lx. Yeah, okay, so my torques now aren't that difficult, now that I've done some geometry here. Just so students don't get confused, I guess I can write that in. So the torques now, the net torque, and I want the net torque, I actually want it to torque in the clockwise direction. So I actually want it to be slightly less than 0. Less than or equal to 0. Equal will be just starting, ready to move, and if it's at all in the negative direction, it's going to torque in the clockwise direction. So I can say, let's see, so torque 1, let's say the torque caused by the weight. So I'll write torque caused by this weight is equal to the weight itself. This is my, I'm going to use this form of the torque equation. The weight itself times the effective perpendicular lever arm. The portion of this lever arm that is perpendicular to this weight force downwards is Lx, and I figured out what Lx is equal to there using geometry. And that is in the, this is in the counterclockwise direction, so there's a positive value there. So this is a plus value. And then the torque here, the torque caused by this force is equal to the force itself, and it's perpendicular to this portion of the lever arm, which is Ly. And Ly, I figured out, was equal to this entire radius minus h. So those are the two torques, and that's going to be in the clockwise direction, which is negative. So put those two torques together, add them up, and they should just be less than 0, just slightly less than or equal to 0 in order for it to even think about starting to go up there. Right, that's the answer for when the force is down there. I think that's enough for now.